So are you experts at the 3 reservoirs now?
Close enough.
Hopefully. I had intended for us to have a quiz today, but I just got tied up with other things, and so we're not having one today, but we're definitely due for a quiz. We probably won't have it on Friday either, since that's a recorded class meeting, but I bet we have one next week, just to give you a little bit of advanced preparation. Next week we are going to be starting on something that is going to require you to have Excel available. So definitely bring your laptop computer to class next week. We're going to be learning a method for determining flows through a pipe network called the Hardy-Cross method. So you can solve that method by hand, but I promise you don't want to. All right, so homework 4 is posted online now. You've got a week to solve that one. It's only 2 problems, but they're longer than average problems, I guess I'd say. The first one you can start after today's class meeting. You know, we'll learn, actually today's class meeting would allow you to start both of those problems. The second one's pretty complicated, and I emphasize in the handout that you really should read the instructions that I provided before you try to solve the problem, because every year inevitably some people apply the Hardy-Cross method to the second problem, and it's not a Hardy-Cross problem. It's a Nodal method problem. So we'll talk all about the Nodal method today. Anybody have questions before we begin? All right. So remember, we've talked about fully turbulent flow before. That assumption that the flow is going fast enough through the pipe that the Reynolds number is high. And if the Reynolds number is very high, then it's just the relative roughness that dictates the friction factor. So we can simplify the Jane equation, for example, by eliminating this second term inside of the logarithm, and it simply becomes this. And so it's an approximation for F that's valid when the flow rates are high. We could do a similar thing with the Colebrook equation if we wanted to. You know, the Colebrook equation could be simplified to look like this if we eliminated the second term in which the Reynolds number tends towards infinity. So if you have a really large denominator, that means that this second term is basically 0, so we might as well not even have it. That's the idea with the fully turbulent flow assumption. And this assumption is one that we're going to apply today when we don't yet know what is the velocity through a pipe. So we'll begin by estimating the F value according to the fully turbulent flow assumption. And then remember that once you've applied that assumption, you need to check it, because sometimes it'll be true that the velocity is really high and that F value only depends on the relative roughness. But in other cases, that won't be true. And you'd have to do a second set of calculations with updated F values that are based on the velocities you determine. So we've done this method of assume, calculate, correct on several prior occasions, and we're going to do it today as well. Now, here's the Nodal method. You've been applying the Nodal method maybe without even recognizing it. You did in the homework assignment you just solved in the 3 reservoirs equation, the 3 reservoirs type problems. Remember, we looked at the junction where those 3 pipes came together. And what we said was we know that the flow into the junction equals the flow out of the junction. So that was one of the convergence criteria that you were checking when you solved 3 reservoirs problems, is you were looking to see if the flow in equals the flow out. And if it doesn't, then you knew that you needed to make an adjustment to either your guesses of the F values or, more probably, the amount of head at the junction. So checking the flow in and the flow out is an important tool that we'll apply on a lot of problems. And so the basic principle just says that if we have a junction where there's no potential for storage, that the only option for an incompressible fluid like water is for the flow to go out of the junction. Now, it's a different story if we have a tank. If we had a tank and there's flow going in and flow going out, in doesn't necessarily equal out if we have some potential for storage inside of the control volume. But that's not what this is. This is a sealed junction with no capacity for storage, and so flow in equals flow out. So what you can see is I've written the equation here, QZ, which is the outflow from the junction, is equal to QX plus QI, which are the two inflow streams coming into the junction. Couldn't be any simpler, really. Now, the application that we're going to use today is a situation like this, where we have water that's going through a single pipe, and then it splits, and then it may come back together again. Now this is a top view. So it's not like we're looking at it from the side and there's an upper pipe and a lower pipe. As a top view, maybe this is the northernmost pipe and this is the southernmost pipe. You may be asking, well, why would they do something like that? Have a pipe going and then split and then come back together again. So can anybody think of a real-world application of something like this where a pipe splits and then may rejoin later? Yeah.
Would it be something that's just like as simple as there could be like a giant rock on the ground where you couldn't physically lay the pipe there?
Okay. Yeah, it could conceivably be an obstacle of some sort. It's maybe even more common than that, although that is a possible application. It's as common as water coming into a neighborhood. So think about water coming into a neighborhood would come to the neighborhood from the treatment plant with one big pipe, and then there's lots of branches going to different streets in the neighborhood, and it's typical to have at the end of streets the pipes come back together again to avoid dead ends in the line. Because if you have a dead end in the line, the water quality in that stagnant water at the end of the line gets pretty nasty. You can have inorganic materials like iron, manganese precipitate out, and it could clog valves and fittings. It can be disinfection byproducts, which are organic materials. It could be the formation of biofilms. So it's just, as a matter of good practice, from the water quality standpoint, good to have, if you've got a neighborhood. A lot of towns have some sort of a grid, 9th Avenue, 10th Avenue, 3rd Street, 4th Street, and so on. So if you have the water coming in, anytime the water's flowing here and going to there, it could also go from here to there. So having a grid pattern also provides you with redundancy in case there's a pipeline break. So if you just had a dead end to different parts of the network, then if one of the junctions breaks, then all of the houses downstream from there lose water. Whereas, like if this pipe broke, people here can still get the water through that route. So we can just accept that sometimes water would be flowing through a pipe, split, and come back together again. So that's what's happening here. And what's tricky in a situation like this is we know what the flow rate through the single pipe is, but we don't know how much of the water goes through the northernmost pipe, B, versus how much is going to go through the southernmost pipe, C. And there's a lot of reasons why we want to know the flow rate through the pipe. We want to know the flow rate through the pipe, for example, so that we could predict what is the pressure at the downstream junction. If we knew the pressure here, and we want to know the pressure here, downstream, for example, because we want to know if people are going to have a pleasant showering experience where they have a nice steady flow coming from the shower head. Or we want to make sure that it is above that minimum threshold required to prevent contamination. So we want to know the pressure downstream. We have to know the flow rate, because all of the models we use to determine the pressure downstream depend on some understanding of what's the flow rate through the pipes, whether it's the Darcy-Weisbach equation or the Hazen-Williams equation, both of those, to know how much energy loss there is through the pipe. You have to know either the flow rate or the velocity, and actually, if you know one, you know the other, because they differ just as a function of the cross-sectional area. So, how much will go through the top pipe? How much will go through this lower pipe? That's the problem we're going to be solving today. So how do we solve that problem? Well, the nodal method is going to be one of the tools that we use, because we could express the flow rate through pipe B in terms of the flow through pipe A and the flow through pipe C. So what we're saying in this first equation is, if QA is known, then QB is however much flow there was going through A minus the flow that was going through C. Okay, so we're expressing QB in terms of QC. And vice versa, we could say that QC is QA minus QB. So this is, although it's written in terms of two different pipes, this is effectively just one equation, because we've just algebraically rearranged this one to get that one. So these are the same equation. You've heard the phrase before, two equations, two unknowns. Then you can actually solve both of the unknowns if you have two equations that express those two unknowns in some different way. This is, we've got two unknowns, but only one equation so far. So we've got two unknowns, unknown through B, unknown through C, but one of the equations we're going to use to solve this conundrum is that together those two flows have to equal QA. All right, so keep that in the back of your mind. I'm going to tell you what's the other equation we use to solve the scenario. And to tell you about that equation, I want to give you the analogy of a ski resort. Winter Place is the only ski resort I've been to in West Virginia. It's down by Beckley. Has anybody been to Winter Place before? A couple of people. All right. So you're familiar with the fact that there's multiple runs there. You can get down the hill either the scary way, like the plunge or nosedive. That looks steep, right? And the way that they characterize the difficulty at ski resorts is green is easy, blue is medium, and then the black diamonds are the ones that are steep and require more expertise. So if you are going from the top of the mountain down to the mountain house, you can go down nosedive, which would be a pretty steep run, or you could take woods run, which is along a ridge line, and it's classified as more difficult than easy, but it's less difficult than nosedive. What do you think makes woods run easier than nosedive? Why is it easier? Is it because the snow is less slippery there?
Elevation change over time.
Elevation change over time? You've almost got it exactly. The slope. So it's elevation change over distance. And of course, velocity and distance are related as time. So yeah, it's the slope. So nosedive is steeper than woods run. So if you stood at the top of the mountain and you went down to the mountain house, this is the start and this is the finish, you'd go at a high velocity on nosedive, and you'd go at a lower velocity on woods run, but you'd end up at the same location. So think about your energy. Your potential energy at the top of the mountain is related to your elevation. And once you've come to a stop at the mountain house, your potential energy is again related to your elevation, but the elevation change is the same regardless of which route that you went. So your energy loss, it doesn't matter whether you go on the steep run or on the shallower slope run, your energy change is the same. So how does that relate to this? Here's what we know. Some of the water will go through pipe B, some of the pipe will go through pipe C, but regardless of which route you take, the energy loss is the same. So let me illustrate it this way by stepping you through a couple of hypotheticals. Let's say, for example, what if both pipe B and pipe C had the same length? And what if they had the same diameter and they were both made out of the same material? So what that means, if it's the same material, they've got the same equivalent sand roughness. So what would the flow distribution be if those two pipes were identical in every way? How much would go through one versus how much would go through the other if the pipes are identical? 50-50. There would be no reason for it to be anything other than 50-50. It would be impossible. So the flow would be split equally if the pipes were the same. Okay, good. Now what if they both have the same diameters, the same pipe length, but then B is more rough? So which would have more flow if pipe B was the rough pipe? Let's say it's cast iron, whereas pipe C is plastic. So which pipe would have more flow if pipe B is more rough? Pipe C. Why? You're right, but why?
Because there is less friction between the water and the walls of the pipe to slow it down.
Good. There's less friction, so there's less resistance to flow. So if pipe B is more rough, does that mean that no flow will go through pipe B? Does that mean it'll like completely stop and it'll only go through the plastic pipe? No. There'll still be some flow going through B. It's just that there will be less. Like how much less? It'll come into equilibrium so that the head loss through each route is the same. So there'll be some flow through pipe B, some flow through pipe C, but the Q through each of them will be whatever flow rate is required to make it so that the head loss due to pipe friction, here's the Darcy's law equation, the flow rates will come into equilibrium so that the head loss through pipe B is the same as the head loss through pipe C. So it's not like the pipe is thinking, it's just that the flows naturally have to be in a head loss equilibrium because they're coming back together again, and it would be impossible for them to have a different energy level and then come back together at the same point. Just like think about the mountain. It would be impossible for you to go down Woods Run and be at the mountain house and then be at a different altitude as your friend who had taken plunge. You're going to be at the same altitude if you're at the same location. So in the case of this pipe, the pressures are going to be the same when these two pipes come back together. The pressures will be the same, so the energy is going to be the same, regardless of which route you take. All right, so we've talked through these first two. Just to really solidify this, let's consider another one. What if the diameter through pipe C is bigger? Now think about how does diameter affect things? If you've got a big diameter, does that mean more flow or less flow will go through? Okay, so bigger diameter in C, same lengths between them, and the same pipe material. So which will have more flow? James? If pipe C is the bigger diameter compared to pipe B,
Pipe C will have more flow.
which one?
Pipe C.
Good. Pipe C, yeah. It'd have more flow because bigger conduit, less resistance. All right, now what about this one? Pipe B is a bigger diameter, but pipe B is longer and pipe C is more rough. So these are going in different directions. Like pipe B is bigger means, okay, there's going to be more flow through B. But now pipe B is longer. So that would mean that there's going to be less flow through B compared to C. And then pipe C is more rough. That also means that C is going to have less flow. So we wouldn't necessarily know just from these qualitative descriptions. We'd actually have to run the numbers and see. Because it could be that the length of pipe B is just a little bit longer. Like if it's just a little bit longer, it's not going to have a huge effect. And it could be that it's just pipe C is a little bit more rough. But then the diameter difference is huge. Yeah.
Couldn't there be a possibility where it would work out that they'd have the same flow?
It's possible, yeah. It's possible they could have the same. But we don't know until we run the numbers. So how do we do that? Remember, the key thought here is that the energy loss through either pipe is the same. So we can set the Darcy-Weisbach equation equal to itself. We know that the head loss through pipe B is equal to the head loss through pipe C. So we could write that as the F value through pipe B times the length through pipe B times the velocity through pipe B squared divided by D2G for pipe B is equal to all of those things for pipe C. So that's how we can get our second equation. Remember, if we have if we've got two unknowns, we need two equations to solve them. This is our second equation. Which was the first one? What was the first equation that we're going to use to solve this? This is Darcy's. Continuity. Flow in equals flow out. That was the first equation. This is the second one. By the way, this is the Darcy-Weisbach equation written in terms of velocity. So H sub F equals F L V squared divided by D2G. What if we wanted to write that equation in terms of Q instead of in terms of velocity? Well, then it is FLQ squared divided by D2GA squared. Because V equals Q divided by area, and so V squared is equal to Q squared divided by A squared. Sometimes we're going to write Darcy-Weisbach equation in terms of Q instead of in terms of V. Because sometimes that's what we're trying to solve, is the flow rate, rather than trying to solve the velocity. These are some big ideas here today. Big ideas. All right, any questions so far?
It's like the reasoning has to do with like the pressure equalizing within the pipe.
That's right.
If it was like an open channel, it wouldn't.
Let's see, what would be the open channel analogy of this? The open channel analogy would be if you've got a river that splits and it's going around an island. You know, it does that, the Ohio River. There's Blenderhassett Island. So the water depth is the same whether you're looking at the north side of Blenderhassett Island or the south side of the Blenderhassett Island. The water comes together after the island at the same elevation. So that would be kind of like the open channel equivalent of this thinking, is you couldn't have the water at like different elevations because it's coming back together. So the same thing is true here. The energy loss is the same through either route because when the two pipes come back together, they have to have the same amount of energy. So just to reiterate or phrase it differently, it doesn't matter how you get from 1 to 2, whether it's through pipe B or through pipe C, the total head loss between the 2 points is the same regardless of the route. Now, by now you probably could write the energy equation in your sleep, right? Here's the energy equation, and it looks like I've done the full-fledged version of the energy equation. So I've got the pump head term on the left-hand side. I've got both the friction losses and, what's this one? Minor or local losses. So this is the full version of the energy equation. And at a point, at one location, there are 3 forms that the energy can be in. And I've mentioned this before, that the energy can be in the pressure, the velocity, or the elevation. So we call that the total head at a point. The amount of energy at a point, or the amount of head at a single point, is its pressure head, elevation head, and velocity head. So by this expression, we could say H1 plus H sub P is equal to H2 plus H sub F plus H naught. This is the energy equation. It's not a new equation. It's the same equation that we've been working with. It's just I'm saying, let's call H1, let's have that be all of the head at that location. So it's the combination of velocity, pressure, and elevation. So everybody's comfortable with this, right? All right. So don't freak out. This is just the energy equation. This looks pretty weird. Sometimes I don't know. Sometimes this throws people off. But let's just remind ourselves how this is just the energy equation still. So what we did is we said, let's solve for H2. If H2 is what we want to know, so H2 is H1 plus HP minus HF minus H naught. Okay? It's just the energy equation still. So now let's look at what we've got on the screen here. So H1, all right, yeah, minus the friction losses. So FL divided by D, that looks like Darcy-Weisbach equation. And what is it multiplied by? Q squared divided by 2GA squared. Okay, yeah, that's just the friction losses that we're subtracting out. And now this term here. So we're saying minus K times V squared divided by 2G. So that's the local losses, subtracting out the local losses, and then plus H sub P. Okay, check. That's the energy equation. But why does it look so strange? Well, one of the things that makes this look strange is Q times the absolute value of Q. Like, why didn't we just say Q squared? Like, why Q times the absolute value of Q? The reason why we bother to make that distinction is that when we apply this equation to some of our methods coming up, we want the direction of flow to have significance. And so if the flow is going one direction, it'll be a positive value, but if it goes the other direction, it'll have a negative value. And if we were just going to square Q, then we would lose that visibility as to whether the flow is one direction or the other. But if we do Q times the absolute value of Q, it has the same magnitude effect as squaring it, but it retains the sign. So it would be clockwise or counterclockwise as indicated by positive or negative value. So the reason why we're doing it is just so we can keep track of direction. That's why it's absolute value here. And then the same thing is true for the pump head. Like Q divided by Q, why bother? Like, we don't even need it there necessarily unless we want to keep track of direction. And that's what this Q divided by the absolute value of Q. So we'll get into that again in the future. But for now, this is just saying you could calculate the head at 2. So that's downstream. Remember, the energy equation has direction implied. Location 1 is upstream, where the water is coming from. Location 2 is downstream, where the water is going to. So what this is saying is that the head at location 2 is the head at 1 minus the friction losses minus the local losses, although it says plus here, that's inside the parentheses. And so we're subtracting the friction losses, we're subtracting the local losses, and then plus however much head is added by the pump. All right. So case closed. That's the energy equation. Now here are the various terms defining all of the things that we already knew about the energy equation. And we don't necessarily have to express the energy equation like this in the nodal method, but it's good practice for when we apply it in the Hardy-Cross method for pipe loops. Is that door open? Sounds like somebody's having a dental appointment. A rough dental appointment. Okay. So let's say we've got 3 cubic feet per second going through pipe A, and we want to know how much of it goes through pipe B and how much of it goes through pipe C. So here's the process that we're going to go through together to find out how much flow goes through B and how much goes through C. We're going to calculate the total head at location 1, and then we're going to find out how much head there is at 2 in terms of the unknown flow rate through B, the head location 2 through the unknown flow rate at C, and then equate the two using continuity equation. That is, QB plus QC equals 3 cubic meters per second. So we know that together they have to equal 3, and then Darcy-Weisbach equation will tell us how much is going through one pipe versus how much is going through the other. So we'll use continuity equation, and then we could, if we know the pressure at 1, we can find out the pressure at 2 by subtracting the head losses and solving for P. This is just an outline of the process that we're going to go through. All right, so 3 cubic feet per second, and let's say that we know the length of each of these pipes, the diameters. They're all galvanized iron, so that simplifies things a little bit. We've got an equivalent sand roughness of 0.15 millimeters. I've already gone ahead and calculated the F value for pipe 1 and pipe 4. You can see the F values there. But we've got a question mark. We don't know what the velocity is through pipe 2 or pipe 3. So why does it matter that we don't know the velocity? We can't calculate the F values using the full Jane equation if we don't know the velocity. Why don't we know the velocity yet? Well, because we don't know how much is going to go through one of them versus the other. Because the flow distribution partly depends on the roughness, but we don't know the roughness until we know the flow rate. So we're in this classical conundrum. So we're going to start with our guess of the fully turbulent flow assumption. So fully turbulent flow assumption is going to be that the F value for pipe 2 is 0.0149, and through pipe 3 is 0.0157. So let me just bring up my PDF file, because I do want you to do some of these calculations, but just in view of the time that's available, we'll skip to the part where you already have the F value. So let me get the examples up. I've taught this course a lot of times. This is just the times I've taught it at Marshall. I've also taught it other places too, so I really love this subject. I hope you get to go through it multiple times, although maybe not this many. I don't hope you fail the class. I'm saying I hope that you get to practice this in your career, and you'll lovingly refer back to your notes and refamiliarize yourself with this and that. So, all right. What's that?
You're saying that like recording the lecture, you don't ever hear that on YouTube.
Yeah, I don't want all my YouTube people to hear how much I hate teaching this class. You can tell I hate it, right? I'm miserable. All right. So here is the, that's sarcasm. Some people don't get sarcasm. I love this class, I really do. All right, here's the F values. We're just applying the fully turbulent flow assumption. So, you know, the normal Jane equation would have the Reynolds number term, but that's been omitted. So here's the abbreviated Jane equation that I've used to give us these initial guess of the F values. Okay. So what I'm going to do is I'm going to pause and ask you to calculate what is V2 in terms of V3. So let me just kind of lay it out on the whiteboard here. The head loss due to pipe friction through pipe 2 is equal to the head loss due to pipe friction through pipe 3. So what that means is the F value through pipe 2, F L V squared divided by D 2G is equal to F3 L3 V3 squared divided by D3 2G. All right, so we know everything we need to know to do a bunch of substitutions in here and get F2 in terms of F3. So what I want you to tell me is F2 is what in terms of V3. So it'll be some coefficient. It'll be a number times V3. So substitute in the initial guess of the F values along with the given length, the given diameter, and you know for G it should be 9.81 meters per second squared. All right, so I'm going to pause, stop talking, and allow you to calculate and find what is this coefficient that relates V2 and V3. So we substitute in everything we know. I guess it looks like I algebraically rearranged everything to solve for V2 in terms of all the other coefficients. So if we make that substitutions, the diameter, the F value, the length, velocity unknown. Now that's squared, but it's in the square root, so it's going to go just to V3. So V2 is 1.204 V3. All right. Why are these two equations equal? Like, why does the head loss through pipe 2 equal the head loss through pipe 3?
Because they're meeting back together.
Because the flow will be such that the head loss is equal, regardless of route. Okay, so we know both equations now. Two equations, two unknowns. We know V2 is 1.204 V3. All right, we know that, and we also know that Q, let's go back to the diagram here. We know Q1 is 3 cubic meters per second. And that is equal to Q2 plus Q3. So in other words, Q2 plus Q3 is 3 cubic meters per second. But we know the velocity, the relationship between pipe 2 and pipe 3 in terms of velocity, not in terms of flow rate. We could have solved for it in terms of flow rate, but what do we do if we know the velocity ratios, but then continuity is expressed in terms of flow rate? No big deal. We can handle that. We just say A2 times V2 plus A3 times V3 is equal to 3 cubic meters per second. So here's one equation that we know, and here's an independent equation that we know relating V2 and V3. And since we have two unknowns and two independent equations, that means that we can solve for both of the velocities. So if we do that, so here I'm substituting in. Can you see that in the back? Is that large enough? Make it a little bit bigger. All right, so substituting in the known A2, 0.1963 meters squared. And then for V2, instead of writing V2, I just put 1.204 V3. Because that's what we found V2 is. So I'm substituting, instead of V2, I want to write it in terms of V3, because I'm going to leave the other one as V3. So then there would only be one unknown in this equation, and it'll allow me to solve for V3. So I put in the expression for V2. I leave this one as V3. And so that gives me the velocity in pipe 3, 8.29 meters per second. And with that, I can determine V2, because V2 is 1.204 V3. So does everybody understand kind of the solution logic here of what we did? I'll pause for a second so you can copy these numbers down. velocities, how can we find out what is Q2 and what is Q3 if we know the velocities? That's right. Multiply it by the area of each pipe. So if we know V3 is 8.29 meters per second, if we multiply that V3 by what we know for A3, here's A3, 0.1257 meters squared, then that would tell us Q3. And so that's what I did here in this step, is found the flow rate through each of them. This is a good time for us to check and make sure the continuity is honored, that the total flow of each pipes together should equal 3 cubic meters per second. If it doesn't, that means probably we made a calculation mistake somewhere along the line. Because the way the process that we went through, it should force that the combined flow rate is equal to what we knew from before as 3 cubic meters per second. So it does. If we add those two flow rates together, it'll equal 3. All right, great. So are we done? Well, remember that we determined the F values using an assumption that we don't know whether or not that assumption is actually true. So we have to check the fully turbulent flow assumption to see, is it actually true? So what that consists of is, now we know these velocities, we could calculate the Reynolds number and determine the full F value using the entire Jane equation rather than just the abbreviated version of the Jane equation, which is omitting the Reynolds number. So this next step is we need to check the validity of the fully turbulent flow assumption. Okay, well, let's check it. Let's check and see. So I calculate the Reynolds number through pipe 2, the Reynolds number through pipe 3, and using the full Jane equation this time instead of just the abbreviated version, then it's saying, for example, the F value through pipe 2 would be 0.01498. And what was it originally? Let's see. Our original guess of F2 was 0.01493, and F3, according to fully turbulent, was 0.01567. This is the fully turbulent assumption values. So these updated values, how different are they? Well, not very different. It's good to maybe calculate it in terms of a percentage. So how different percent-wise is pipe 2, for example? So if I have the new, this is the good guess now, this is the correct value because it's been updated. So if I have 0.01498 minus the initial guess, 0.01493, and then divided by the new one, which is the correct one, 0.01498, and then multiply by 100, it's 0.3% different. So if it's changing, if your F value is changing like less than 1 or 2%, then you don't need to go through this process again. Like if we redid these calculations, like if I took these new F values and substituted the new ones back up to here, so if they were kind of different, then what I'd do is I'd substitute the new F values in here. So I would correct that F value, this one I'd change, this one I'd change, and I'd get a slightly different ratio. You know, it'd say 1.201 or something like that. It would be slightly different, and it would give me slightly adjusted velocities. But here, where the F values are less than 1% different, then we can just say the solution is converged, the pressures, the flow rates are what we calculated. All right, so what we're going to talk about on, I guess, Monday of next week or in the recorded lecture, I'll step you through some hints for the homework. This is the homework problem that you've got. Instead of 2 pipe paths, there are 3. But that actually doesn't complicate things as much as you might expect. It's the same equation. It's the same process. So if we want to find out the flow distribution through each of those pipes, it's the same approach as what we just solved. So there's some suggestions that I've offered on a step-by-step basis if you want to get an early look at that. All right, remember Friday's class is just a lecture video, so I'll see you face-to-face on Monday of next week. Take care.